Okay, this is a 5.5 review, day 1, so 1 through 30. First, we're going to decide whether it is one-to-one. Remember, it has to pass the horizontal line test for it to be one-to-one, so no, it does not. Number 2, no, it fails the horizontal line test. Number 3, no, it fails the horizontal line test. Number 4, if we look at the graph of number 4, it's going to look like this. Okay, and it'll keep going out like this. So yes, it will pass the horizontal line test. Number 5, it's a quadratic, shift it up 1. No, that fails the horizontal line test. And number 6, absolute value, 2x plus 7 is a v that opens up from over here. And that also is a no, it fails the horizontal line test. Okay, so none of these that are no's would have inverses, right? They has to be one-to-one to be able to have an inverse. Okay, so for number 7, we're going to look at this equation right here. Y is equal to the cube root of 2x minus 7. So let's get a graph of that. Okay, I just put that into Desmos, and the graph looks like this. Okay. So number 7 is the domain. So the domain is going to be all this way and all that way, so all real numbers. Or you can write it as interval notation. Number 8, the range, goes up, 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 and down, down, down. So it's going to be all real numbers, or an interval notation from negative infinity to positive infinity. Number 9, why does it exist? Okay, why do we have an inverse? The inverse exists since it is one-to-one. Remember, all these that did not have, right, these would not have inverse. Yeah, it has to be one-to-one to be able to have an inverse. Number 10, formula for the inverse. Okay, so to find the inverse, we got to switch the x and the y. Okay, so we're going to cube both sides and subtract your 7. Sorry, add your 7 and divide by 2. Okay, so there's number 10. Number 11 says graph both of them and describe how they are related. Okay, so I already knew this one would look like this. Okay, the other one's going to look like this. Okay, so how are they related? Number 11, they are reflections across this line y equals x. And number 12, verify that they are inverses, so I have to find the composition of the original and the inverse, and it should equal x, right? Going both ways. So for number 12, basically part A, was f of f inverse. Okay, so I'm going to take the inverse, which is this one right here, and I'm going to plug it in up here. So it's the cubed root of 2, and I'm plugging this in, minus 7. Okay, so when I work this out, multiply this through here, that would just be the cubed root of x to the third plus 7 minus 7. Those cancel out. We have the cubed root of x to the third. Those cancel will just give you x. For part B, I want to find f inverse of f of x. So I'm taking the f of x function and plugging it into my inverse function. Okay, so taking this, plugging it in here. So that's going in for the x. So the cubed root of 2y minus 7. Sorry, here's my original, right? 2x minus 7, not y. Cubed plus 7 divided by 2. Okay, so the cube and the cube root cancel. So 2x minus 7 plus 7 over 2. Those two cancel, it's 2x over 2, and divide gives you x. So yes, they are inverses. We did it correctly. Number 13, you want to match these graphs here. Okay, basically it's just, it's using a to the x, okay, and where does it move? So if it's plus 2 up top there, it moves left 2. Okay, so if you think about this, the original graph is just y is equal to a to the x. When you graph that, it's going to go through at 1. Okay, so if it's moving to the left 2, this point is moving to the left 2, which means this point, like crossing here, is going to get higher, right? Okay, so this one right here, okay, at 1 it'd be over here. Number 14 moves up 2, so we're taking this graph right here and it's moving up 2, so it's going to go through at 3. So right there. Number 15 moves up 2, but it also reflects over the x-axis. Okay, so instead of opening like this, it's opening like this instead, reflecting over the x-axis, and it also moved up 2. So 15 is D. And 16 moved up 2 and reflected over the y-axis. Okay, so reflected this way and moved up 2. Okay, number 17. Okay, if you're looking at this here, we know it's not growth, it's decay. So what does that A have to be for it to be decay? Well, it has to be a number between 0 and 1. So number 17, that A has to be between 0 and 1. Number 18, the domain of this, it keeps going this way, it keeps going this way. So all real numbers, negative infinity to positive infinity. 19, the range. Okay, remember there's an asymptote right here for an exponential. So my so it's going to be from 0 and above, so 0 to infinity. Okay, you can write it either way, it's fine. Number 20, find the value of f of o. So if I plug a 0 in there, so 0, if x is 0, my y is, right here, 0, 1. I want to graph it by hand. Okay, so if I think about this right here, right, I know it's going to have to be the reflection across this line y equal x, right? Okay, so it has to be reflected across this y equal x. So this point becomes this point. If it gets really close here, it's going to get really close up here, right? Okay, so the graph, and this point here will become this point over here. So it comes like this. Okay, so this here is the same as this here, and that part there is a reflection of that part there. Okay. 22, actually find it now. So my original graph was y equals a to the x. So the inverse is x going to be a to the y. To solve for that y, I got to use the opposite of exponent is a log. So turn this to a log function. So it's log base a of x equals the y, which is our inverse. The y is the inverse part. Okay, there's up through 22. Number 23. I'm going to graph it and then find the domain and range. Okay, so number 23, we have f of x is equal to 1/2 to the x minus 1. Okay, I know it's exponential decay, so a lot of the times you can graph these knowing what it is, so it's exponential decay, and it's shifted to the right one. So instead of going through 1 here, it's going to be right there. So we have exponential decay going like this. Okay, so in this one here, our domain goes all the way this way, all the way that way, so all real numbers. And our range, there's an asymptote right here, so it's 0 and above. So our y has to be greater than 0, or from 0 through infinity. Number 24, f of x is equal to the x plus 2. Okay, so thinking about what this is an exponential. E is like 2 point whatever, so it's exponential growth. And plus 2 just shifts it up 2. So my asymptote, instead of being at 0, is being shifted up 2. And this point from 1 goes up to 3. Okay, so there's our graph. Our domain, once again, goes this way and this way, all real numbers. And our range now goes from 2 through infinity. F of x is equal to negative 4 to the x. Okay, 4 to the x is exponential growth, but it's negative in the front. So instead of being here, it's reflected across this axis here, so it's going to look like this. Domain, once again, all the way here, all the way here. Range, okay, our asymptote didn't move anywhere, okay, but it's now below, so our y's are less than 0, or from negative infinity to 0. Okay, number 26 says, okay, if I have this, A, and A is this, okay, so A is between 0 and 1, so it's exponential decay, and decay that is flipped across the y-axis, okay, so exponential decay is like this, right? But if it's a negative, it's flipped across the y-axis, so it's instead of going to flip across here, so it's going to look more like this, right? Okay, so it looks pretty much like an exponential growth then. So is it increasing or decreasing? It is increasing. Okay, you can also use Desmos to just kind of get a visual for it. You know, put A as any number like a half or something and raise it and see what happens to it. Okay, number 27. You want to solve these analytically and then use the graph in Desmos to get the next part. So we have 1/8 equal to the negative 2x is equal to 2 to the x plus 3. So with these here, we can think about getting the same bases. I guess you could probably use, yeah, okay, we'll just get the same bases. So 1/8 is 2 to the negative 3. Okay, so I multiply these exponents, so I get 6x. Now that I have the same bases, I know that 6x has to equal that x plus 3. So x is equal to 3/5. Okay, now, so that's part A. Part B, I'm going to graph 1/8 negative 2x minus 2 to the x plus 3. And I want to know where that's greater than or equal to 0. So let's go to Desmos and graph it. Okay, this is what that graph looks like. I have the asymptote here that it gets closer and closer there. Anyway, we don't need that part. But here's the 3/5. Okay, that's where it's equal to 0. So where is it greater than or equal to 0? Well, from 3/5 through infinity. Okay, and actually it's we're equal to, so it can be equal to here as well. So we should have that there like that. Okay, number 28. 3 to the negative x over 27 to the 1 minus 2x. Okay, same basis could be 3. So we have 3 to the negative x. This is 3 to the negative third. Okay, bring it up top with the negative, and 3 times 3 times 3 is 27. So if I distribute this through, it would be negative 3 plus 6x. Okay, now I have the same bases. I know this negative x has to equal negative 3 plus 6x. So I know 7x has to equal 3, so x equals 3/7. Okay, then I will, part B, take 3 to the negative x and subtract this. In Desmos, whenever you have this, make sure you put that in parentheses so it'll stay up there. Okay, so we'll look at the graph here. Okay, putting that into Desmos, we get this. And where is it less than 0? So from our 3/7 through infinity, it's less than. So from 3/7 through infinity. Number 29. 0.5 to the negative x equals 0.25 to the x plus 1. Okay, now let's look at these as fractions. So this is 1/2 to the negative x. This is 1/4 to the x plus 1. This is 2 to the negative 1. And this is 2 to the negative 2. Distribute it through, you have 2 to the x on this side. Here you have 2 to the negative 2x minus 2. Since we have the same bases, I know that x has to equal negative 2x minus 2. So 3x has to equal negative 2, so x is equal to negative 2/3. Okay, so for part B, 0.5 to the negative x minus 0.25 to the x plus 1, and let's see, we want it to be greater than 0. Okay, so I'm going to graph this on Desmos. Yep, by looking at this graph here, you can see there's an asymptote right here. Okay, so it never touches, right? There's never going to cross your x. Whereas at less than 0, all the way from negative infinity through positive infinity, it's always going to be less than 0. So I had a little snafu with my video. So anyway, I'm going to pick up from here. So this is the graph for this here. So we can see where it's greater than 0. It's from this negative 2/3 all the way through infinity here. For all those x's, it's always greater. Okay, so number 30. Okay, take it step by step. First thing I would do is turn these into fractions. So 0.4 is 2/5. 2.5 is 5/2. Notice they're just reciprocals, right? Okay. So you can make them 5/2 or 2/5. Either way, I made them 2/5. So keeping that the same, this is that to 2/5 to the negative 1. And if I distribute that negative through, you get this. Now I know that x has to equal this, and then you can solve. Now, notice the x's cancel out here, don't they? So there really is no solution to this. When you go and subtract this over to the other side, graph it on Desmos, you get this graph, and you can see from that graph why we have no solution. Because when you graph this, there's an asymptote right here where it will never cross or touch 0. So it's never 0, never answer. So where is it less than 0? It's always less than 0. So all the way down here, all the way up there. So for all x's, is it less than 0? Now, also, just kind of, with all these 4 problems, you could use the log function. So for example, if you took it and did this one, you could say the log of 0.4 to the x is equal to the log of 2.5. With these last 4 problems, you could have also used the log idea. So we can say log of 0.5 to the negative x is equal to log of 0.25 to the x plus 1. Use the power rule, so negative x log of 0.5 equals x plus 1 times log of 0.25. If I distribute that through, that's x times log of 0.25 plus log of 0.25. I want to get these x's together, so I'm going to bring them both to this side. So x of log 0.5 plus, if I bring this over, it's plus x of log 0.5. And if I bring this number over there, I'm going to subtract it over. And if I factor out an x, and to get x by itself, I just divide by this number. So x would equal negative log of 0.25 divided by log of 0.25 plus log of 0.5. If you put that in your calculator, it would come up to be negative 2/3. So notice we get the same answer when we work it out with getting the same bases as well.